Okay, welcome to this lecture where we will talk about the basic notions of representation theory in a general finite group. So we will give a very short introduction to this field. We just take the main essential notions that we need to develop the Fourier analysis in the course and just the basic notions of the representation theory that we actually end up using. And the reason why we want to do this, so the kind of motivation for this is basically that we, as I said in the previous lecture, we have these random walks on the group G, and then we have the L1 identity that allows us to connect, for example, the distance of the random walk hitting a set or event A with the cardinality of A divided by the cardinality of the group. By the L1 norm of the iterated convolution and its distance to the uniform distribution of the group. And the reason we want to do this is that then we want to, for example, prove that whether the random walk is, for example, ergodic, for example. So the ergodicity, remember, as in the ZP, means that the distance to the uniform of the iterated convolutions goes to zero as n goes to infinity in the number of iterated convolutions we have. So in order to do this, in the same way we did in the cyclic group of P elements, we need to define the notion of Fourier transform. And but the problem is that in a general finite group, you don't have such a nice, a simple theory for this thing that you can do. You need to kind of extend it slightly in these notions of using these notions of representations. And we will see, not in this lecture, but in the next one, how these representations are used to define the Fourier transform. But just keep this in mind that everything I'm doing now in this lecture is really building up towards getting the Fourier transform defined, so that we can actually understand the random walks in the same way we did in the cyclic group. Okay, so let's call this introduction to representation of G. So basic introduction of this topic now, and the definition, the basic definition here that we want to use is the following: that a representation rho is a mapping from the group G to the general linear transformations of rho G with a vector space V, where this rho is a homomorphism in the sense that what we have is that this rho X, when we take two elements in the group and they get their product, then this is equal to the product in the as matrices. So we will just I will mention in a second what this GLB rho is. That this is true for any x and y in G. And what we have here is that this GLV rho, this is the set of basically all invertible maps, maybe all linear maps V rho to V rho, and this V rho is a finite dimensional complex scalar vector space with an inner product. So it's some vector space with an inner product in it. So for example, we could talk about e.g. for example, V rho could be, for example, some C to the power D, for example. That could be as an example of a vector space with an inner product using the complex numbers. And in that situation, this GLV row consists of D times D matrices, invertible matrices. Because all the invertible matrices are actually identified as invertible linear maps from the vector space CD to itself. So we have this notion of representations. It's just this kind of mappings of the group that for each group element we can assign a linear map, like basically a matrix. But it has to somehow obey the group structure in this way. The homomorphism property is the most important thing here, is that once you add two group elements together, if you want, for example, understand the random walk in the group, then you could just kind of reduce it to these understanding products of matrices because of the homomorphism structure. That's why the representation theory is such a useful way to transfer maybe a slightly more complicated looking group into maybe something which you can manage with matrices a bit better. It's not doesn't solve always everything, but it can be useful. And here the dimension of the representation rho is the dimension dim v rho. So this is a vector space, so it has some dimension. So e.g., like for example, if you have the complex space, we will have the dimension being the dimension of the vector space. So the dimension of the representation is defined to be the dimension of the vector space V that it maps into. So that's the basic notion of a representation. And now the next thing is that we want to restrict to a certain class of representations to do the Fourier analysis, and that will be called unitary representation. So this the representation rho from G to GL V rho is unitary if basically that all the images is in, if for any x in G this rho x is a unitary matrix or unitary map. I.e. that basically means that this rho x is a linear map and it's an invertible, but it basically means that if you take the inverse and if you take the map to itself and you take it from the other side, rho x minus 1, this is just the identity matrix or the identity map if on the group where I could call this I rho. I rho is the identity matrix of V rho to V rho identity. So I rho mapping into V, it's just the V for any V rho. So these are the kind of what we want to use at the unitary representations in the most case. And what is actually possible with the unitary representations is that you can choose the inner product that you have in the V rho to make actually any representation, like you change the inner product in a way that you have it being unitary. So there's a way to actually reduce that all the theory of general finite representations of this type into just unitary representations. So we will now keep on assuming that all the representations we consider are unitary representations. And we can write, if we write this U V rho as the space of all unitary maps in GL V rho. So then basically unitary representations are just mappings into this. So now a rho is a mapping from G into U V rho. That's the other way to say that it's a unitary representation. It's a representation whose the image is always in the space of all unitary matrices. And the final thing I want to mention is this notion of if we have a rho which is a unitary representation, then and we have that we have some W, which is a subspace of rho. So this is subspace, like it's a linear subspace of the vector space V rho, which is rho invariant. That means basically that for any x in G, this rho of x, W, which is just the set of points rho of x, W, where W is in W, this is a subset of itself. So the representation as a linear map, at the point x, you choose a point x, you map it into some matrix, so basically a linear map, rho x, and the linear map is then can act on this W. You get another space, maybe a linear space that it might rotate, but this is the idea is that it stays within this W. So that's an invariant subspace. And we have a unitary representation and we have an invariant subspace. Then the restriction map, which is rho, if I restrict into this W, which is, I call it a map, it's again a map from the group, but we map just to the unitary maps within this W, is called called a subrepresentation. So we can take any representation and a subspace, then we can create a subrepresentation if it's an invariant subspace in this sense. So that means the invariance is just used for the fact that now we know that it always maps all these points inside the same space for any point x, because that's for any group element G in G. Okay, so that's kind of the basic notions of representations that we have here, and maybe some examples would be good to give. So let's take a couple of examples. So one of the first example is something called a trivial representation, which is defined for if we have a V, a finite dimensional vector space with complex scalars and an inner product, then this ID, which I call it IDV, which is a mapping from G into the U of V. Okay, in this case I'll take it into actually, yeah, it's a unitary map, so that IDV at the point x, and if you apply it to a vector V, this is a small v, this is a big V here, V and small v, this is equal to V for any x in G and for any x in any small v in big V. This is called trivial representation. So you can find this like for any group, you can just put in this identity map at every point. So that's one way to represent your action inside the space. But there are many other representations as well. This is like the one that you can always construct. That if you take any finite dimensional vector space with complex kind of inner product and take the unitary matrices here or unitary maps inside here, then you can represent your group inside here as an identity element. So i.e. this ID Vx is the identity matrix of V, the identity matrix or identity map. But the other class which is important are these also called irreducible representations. And we say that a rho, which is a, let's say a UGV, unitary representation, is irreducible if the only row invariant subspace for is either the trivial one, so the subspace is either or the V row. So remember the definition of the row invariant subspace. So i.e. this means that if we have that we have a W which is a subspace of V row and it's row invariant, so it meaning that row x W is inside W for any x in G, then this implies that W is 0 or W is V row. That's what this means. This is an irreducible representation, it has this property. So that basically means that you don't have like non-trivial sub-representations. If you take such a representation, you can't somehow restrict the representation to a subspace and then somehow have the same idea there. So this irreducibility of the whole action we have here. Now that we have like defined the notions of irreducible representations and we got the idea what these situations are, the next topic that I want to talk in the next video will be on we use these irreducible representations to prove a very simple theorem called Schur's lemma, which is a really powerful lemma in this theory actually. And especially when we go to the Fourier analysis, we can do a lot of the kind of analysis, the basic things that we did in the group ZP in a much simpler way by using this Schur's lemma. So in the next lecture, the Schur's lemma will explain that, and we'll give you an idea what that notion is. And it will be related to like comparing basically two different irreducible representations. So I'll see you then. Okay, see you. Thanks.